when we were talking the other day, we were talking about functions and what a derivative function could do to help explain what would be on the graph of the actual function. So when a derivative is positive, the function's increasing. When a derivative is negative, the function's decreasing. So anytime you have a local maximum, it's where the derivative goes from a positive to a negative. And the same thing for a local minimum we could find using the derivative. And then we talked about the concavity. If something is concave up like a cup or concave down like a frown. When something was concave up, the derivative was going from a big negative to a smaller negative to 0 to a positive. The derivative was increasing. And we know a derivative is increasing when its derivative, the second derivative, is positive. So we could tell concavities from the second derivative. So there's a lot of things we can do, and I thought probably before we get on to the next topic, we should talk about a couple of examples. So here's a problem that you haven't seen exactly like that before, but see if we can use our knowledge which we've learned in order to solve it. So find the equation of a tangent line to a cubic. Well, what do we need to find a tangent line? We need a point and a slope. Well, sometimes you're given at least part of the point. This time we're not, but we are given the knowledge that it's at the point of inflection. So in order to get the point, we have to find the point of inflection, wherever the curve changes from one concavity to another. And we know the only way to find that is to go to the second derivative, because that gives us what the concavity is. So before we can get the second derivative, we have to take the first derivative, which is 3x squared plus 6x. We don't need the first derivative right now, at least, but we do need the second derivative. So the second derivative is 6x plus 6. And we know the only place it could have a point of inflection is where the second derivative is 0 or undefined. So to prove that it really is a point of inflection, we have to show that it changes concavity. So if we put this on the number line, if we call this y double prime, we see the only place where this is 0 is at x equal -1. And there's no place where it's undefined. So that's the only possible point of inflection. And we see if we go to the left of -1, the second derivative is negative, and to the right, it would be positive if I picked a number bigger than -1. So I can see that the function itself changes from concave down to concave up. So that really is a point of inflection. So the point is -1. Well, how do we always get the y value? You go back to the original function, which gives the relationship between x and y. So we see y of -1 is -1 plus 3 plus 2, or 4. So we're halfway there. We've got the point for our tangent line. Now to get the slope, what are we going to use to get the slope? Well, the first derivative. And we've already got the first derivative. So all I have to do is plug in -1 to the first derivative. And I get 3 minus 6, which is a -1. There's my slope. Now I can use the point-slope formula to get the equation of the tangent line. Y minus the y value equals the slope, -3 times x minus a -1. And we've got the equation of the tangent line. So, a problem we've never done before, but just using the knowledge we had of what derivatives do, it wasn't too bad. Now, just to show you that it doesn't just work on polynomials, let's go to a trigonometric function. And we'll pick one that we already have a knowledge of what the graph looks like, so we can kind of confirm what our analysis gives us. So let's pretend for a minute that you don't know what the sine function looks like. And I want to know where it has a local max or min. Well, and let's just consider a part of this graph. From x equals 0 to 3 pi over 2, not including the endpoints. I have an open interval, so it doesn't include 0 and 3 pi over 2. Well, to find local maxes or mins, I have to see where the derivative changes from positive to negative or vice versa. So I better first take the derivative. And the derivative of the sine is the cosine. And I'm looking for possible points where there are local mins or maxes, and that's going to be, we've proven that's where it's 0 or undefined. Well, the cosine is never undefined, but it's equal to 0 at many places. It's equal to 0 at pi over 2, at 3 pi over 2, and a whole bunch more places that way, and negative pi over 2, and a whole bunch of places that way. But in our domain, since 3 pi over 2 isn't included, that's the only critical value. Now, to see whether it's really a local max or min, I better put it on the number line. So I put in pi over 2, but I don't make arrows on both sides. I have a domain from 0 to 3 pi over 2. And if I look at the derivative, we know in the first quadrant from 0 to pi over 2 the cosine is positive, but once you get into the second and third quadrants, which is where this is, it's negative. So we see for sure that the function goes from increasing to decreasing, from a positive slope to a negative slope. So we know at pi over 2, and the sine of pi over 2 is 1, so at that point we have a local, you can just look, it's a maximum. And we can now say, since that was the only critical point, that there is no local minimums in that interval. Now I didn't ask it, but what about the points of inflection in this interval? Well, now we would have to go to the second derivative. Well, the derivative of the cosine is minus the sine of x. And possible points of inflection are going to be where minus the sine of x is 0 or undefined. Well, the sine is 0 at 0 and pi, and 2 pi, and negative pi, but the only place inside of here is at pi. So, if we put that pi on the number line from 0 to 3 pi over 2, and call this the second derivative, we know from 0 to pi the sine is positive, so minus the sine is going to be negative. And then once you get past pi, the sine becomes negative, so the second derivative is positive. So we know the function goes from concave down to concave up. So that means there really is a point of inflection, and it would be at what point? Pi, comma, the sine of pi. So I've solved, without knowing what the sine of x looks like, I've solved where it has points of inflection and local maxes and mins, which would help us graph that. Now let's see if it goes along with our knowledge of what the sine does. Well, here's pi over 2, pi, 3 pi over 2. We know the sine starts at 0, goes up to 1. So it goes something like this. And what do we see? At pi over 2, comma 1, we do have a local maximum. And right here at pi, comma 0, concave down to concave up. So it goes just like it should. So I hope that gives us some confidence in how we can use the derivatives to help us find out some things about the curve. Now, every example that we've done so far has been where we've got what the function is, a polynomial or a trigonometric function. But what if we just, instead of having a function, we had a graph of the function? In other words, derivatives really helped us tell us things about functions. Will derivative graphs help us tell something about the actual function? So I've just given a couple of examples. I don't think we have to learn any new concepts. We just have to interpret what we already know. So right here I've got a little sketch. This brown is y equals f prime of x. So we're looking at the derivative graph, and we want to see if we can figure out what the actual graph y equals f of x would look like. Well, one thing that's actually going to be quite important, especially as we get in a couple chapters from now, is just knowing the derivative going to tell us where on the graph the function is. Remember, derivatives only give us slopes. So knowing what the slope is doesn't tell me whether the graph is up here or down here or in between someplace. So really, there's more than one possible answer to this. But we still should be able to get the basic shape, and that's what we're really looking for. So let's just guess. Well, it's not even a guess. Let's just assume that the graph is starting right here at the beginning of our domain. Our domain is just from there to there in this graph. So what do we see at the beginning? For this first x value in the domain, the derivative, if we looked at the y value corresponding to that x value, you'd get a negative number. We don't have a scale, but say that was -4 down there. That would mean the slope at the very beginning is -4. So the function is doing what? It's decreasing. And then it works from -4, it works to -3, to -2, to -1, to 0. By the time you get to this x value right here, we know the y value of this derivative graph is 0. So the slope should be 0. So it's going to go from what? It's going to go from a -4 to -3 to -2 to -1 to 0. What's the slope doing? The slope is increasing. It's going from a -4 to 0. And we could have known that because the derivative is increasing. Whenever the derivative is increasing, the function is going to be concave up. And another thing is, because all the derivatives are negative values from here to here, we knew we had to be going down. So just with our knowledge of derivatives being positive or negative, or increasing or decreasing, tells us what the shape of the actual function is going to be. Well, once we get to here, now, in these next two sections from here to here, the derivative values, the y values of the derivative are positive. So we know the function has to be going up in that interval. And at the beginning, the derivative is still increasing. So I still have to be concave up. But when I get to this point right here, we still have positive derivatives. So I'm still going up, but now the derivative starts decreasing. And we've shown when a derivative is decreasing, the function is concave down. So I'm going to go concave down. The derivative is going to go from a fairly big positive slope. By the time it gets to here, the y value of the derivative is 0, so I have to be at a 0 slope. And now I'm back to negative values of the derivative, so I have to be going down. And I'm still decreasing, so I have to be concave down. And I do that, and I've got the shape of what y equals f of x will look like. And like I said, it could be a little higher up or it could be farther down. And we're not sure, it's possible that it could drop down a little bit farther, but we've got the basic shape of it. Now, there's some really important things we see besides what we've used. Look what we have right here. On the graph, we have a local minimum where the derivative went from negative to positive. That's the first derivative theorem for finding local maxes or mins. Where the derivative goes from negative to positive, we're going to get a local minimum. And sure enough, we do. And where a derivative goes from a positive value to a negative value, we get a local maximum. And guess what else? Where the derivative goes from increasing to decreasing, right here we get a point of inflection, where the function goes from concave up to concave down. So this is really pulling together a lot of really important ideas. Let's try one more. This time, y equals g prime of x is this brown graph, and we're trying to sketch the function. Again, we're not sure exactly where it is on the graph, so let's just start right about here. Now, what do I see at the beginning? The derivative values are all negative, so the function has to be going down, but the derivative is neither increasing or decreasing. All the y values of the derivative are the same negative value. So I know that I'm not going to be concave up or concave down. I'm going to be straight. And whatever the slope happens to be. Say we don't have a scale, but if that was -4 down there, that would mean this slope had to be -4 that whole time. Now, what happens here? Now, the slope quickly changes from a negative value to a positive value. Not quite as big in absolute value. This number here in absolute value is bigger than that. So it's going to have a positive slope and not quite as steep a slope as this. So it's going to go something like that. Not quite as steep. And what do we find out? That right here, what would you say the slope is of the function we just graphed, y equals g of x? It's undefined. And lo and behold, that's what the derivative graph is telling us. It's undefined at that point. The slope changes really quick from one slope to another slope. And that's also a place where you get a local max or min. In that case, we get a local minimum because it's going from a negative to a positive. So, let's just go from two simple examples to one really complicated one. At least it looks complicated, but as long as we do it step by step the same way, there's only two things we really have to look at on the derivative graph. So we're looking at this function right here, which is y equals f prime of x. And we're trying to sketch the function, just like we did back here. Now, where do we want to start? Again, it's just the derivative graph, so we could start anywhere. So let's start right about here. Say that's the beginning of the domain, and this is the end of the domain. Now, one thing that might help you is say, when are we going to have changes on this graph? Every time the derivative goes from positive to negative, something interesting happens. So here, the derivative is negative, and here it's positive. So you could just draw in a little dotted line to tell you something important is going to happen there. It's going to be pretty much the same from here to here. Well, where is another place? Right here it goes from positive to negative. Right there it goes from positive to negative. Even right here, it goes from positive to negative. and then right here, and that's the last time it goes from positive to negative. Well, what's the other important thing that happens on a graph of the derivative? Every time a derivative goes from increasing to decreasing, there's a change in concavity. So right here's going to be an important change. Then it goes concave down, and then it goes increasing and then decreasing, and now it's back to increasing again. Now here it goes from neither increasing or decreasing to increasing. So that's also got to be a change. And here it goes from increasing or decreasing to increasing. And then this just looks like a place where something interesting is happening because the derivative doesn't exist at that point. So we've got all these little sections that we have to do the same way we did this over here. So I'm going to start here, and what do I see? The derivative is negative, so I have to be coming down, but it's increasing, so I go concave up. So decreasing and concave up. And look, I have a zero derivative there, and sure enough, I get a zero derivative. It looks like anyway. Now, what happens in this next section? The derivative values are now positive, and the function and the derivative is still increasing. So that means I have to go on the function, I have to be increasing and concave up. So increasing and concave up. And again, I wouldn't say you're wrong if you went up to here. Basically, you're just trying to get the shape. The derivative values in this section are still positive, so I'm still going to be increasing with my function, but now the derivative is decreasing. So I have to go concave down, and guess what? By the time I get to here, the derivative has to be 0. So I have to flatten right out at that point. Now, in this next two sections, we have negative values for the derivative. So the function has to be decreasing in both of these places. Now at the beginning, since the derivative is decreasing, the function's going to be concave down. But then when we get to this point, now the derivative values are increasing, so I have to go concave up. And sure enough, I have to get to a zero derivative by this point. So I go concave up to a zero derivative. In this next section, I have positive values of the derivative, so the function's going to be increasing, and it's still increasing, so I'm concave up. Now, we hit an undefined derivative. This is kind of interesting. We're at a positive slope at this point, and then all of a sudden, all the derivative values become negative. So there's not a gradual change from positive to negative. It goes really quickly from a positive slope down to a negative slope. So I'm going to have to start going down this way. And since it's neither increasing or decreasing, there's going to be no concavity. It's going to stay at whatever this slope, whatever this negative value is, it's going to stay at that. So it's just going to go down like this. And sure enough, look at the slope of our curve. It's undefined. I would not want to touch that. I would scream if I touched that. You don't want me to do that. And that's what the derivative is telling us. It's undefined. Now what happens? Now we're still decreasing in this section because the derivative values are negative, but now the derivative is increasing, so I'm going concave up until I get to a zero derivative. So I want to get right up to a flat slope at that point. In this next section, I have positive values. So I want to be increasing, and the derivative is increasing, so I'm concave up. So I go concave up. Now this next part is going to be a little bit hard to draw. I'm going from a positive slope, but not gradually getting to a more positive slope. I really quickly jump to a more positive slope. So say that's a slope of 1, all of a sudden I'm going to go to a slope of higher than 1. So right here, you're also going to have a sharp point. It's a little harder to see than this one, but it's really quickly changing slope. So we do have an undefined slope, because you wouldn't know whether it was this slope or this slope, depending on which direction you're coming from. Now, what happens in this whole section, the derivative is decreasing, so I start out at that higher slope, but I'm going to go until I get to a slope of 0. Right? I'm concave down because the derivative is decreasing. Now I get to a 0 derivative, but guess what? Instead of starting to decrease, I can see that now it's going back up again. The derivative is increasing, so I'm going to go concave up. And I'm done. That was a long one, but it really wasn't done any different than the smaller ones. It was just done step by step. Now, just a couple of points before we leave this problem. Where do we know we have our local minimums? There's a local minimum, there's a local minimum, and there's a local minimum. Well, what should happen at local minimums when the derivative goes from a negative value to a positive value? Well, here it is. Negative to positive. Right here. Negative to positive. Right here. Negative to positive. So anytime that happens, you're going to get a local minimum. Here's our local maximums. That's when the derivative goes from positive to negative. Oh, and here's another one. There's a local maximum. This time the derivative went from positive to negative, but not gradually. So where do we find local maximums? Where the derivative is 0 and where the derivative is undefined. So all of these ideas are making sense on this graph. And where do we get points of inflection? We kind of know you get points of inflection wherever the derivative goes from increasing to decreasing. Well, here it goes from increasing to decreasing. And sure enough, concave up, concave down. There's a point of inflection. The derivative goes from decreasing to increasing. Right here. What do we see? Another point of inflection where it goes from concave down to concave up. So, anytime, here's another one. Decreasing to increasing. Right there we have a point of inflection on the graph where it goes concave down to concave up. So even though we had a 0 derivative at this point, we still don't have a local max or min because it didn't change from positive to negative. Now, without doubt, for most of you, it's going to take some practice doing these. But as long as you keep in your head those basic concepts and go step to step, you're not going to have too many problems doing that with a little bit of practice. Okay, so one last way you could use these same concepts. Here's a way you could be tested to see if you understand it. You could be given y equals f prime of x, the derivative graph, and asked to give intervals on the actual graph where f of x is increasing. Well, I can do the explanation before I even answer it. Where are you going to get places where f of x is increasing, where the derivative is positive? So I can say, I'll do my explanation. Because f prime of x is positive. That's my reason. Now, what's the intervals? I go back in here, and where is f prime positive? Well, it's positive here, goes down to 0, then it goes positive. So all the way, and there's an arrow there, so anywhere to the left of -1. So I can say x less than -1. All those places, the derivative would be positive. And then again, once you get to 2, all the rest of the time, the derivative values are positive. So x greater than 2. So we've answered that without actually graphing, because we could do the same thing we did up there and graph and see what the function looks like, but I don't have to. I can just interpret. Let's do it on number 2. Give the intervals of f of x that are concave up. Well, think, what does it mean for a function to be concave up? When we've got the derivative. The derivative has to be increasing. So I can give my answer first. Because f prime of x is increasing. Maybe you should say for these values of x. Just to be clear, you could say the same thing up there. F prime of x is positive for these values of x. Well, where is f of x increasing? Not here, it's decreasing, but from -3 to -2, it's increasing. So I can say -3 is less than x is less than -2. Well, any other places? Well, it goes decreasing, 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 but once you get to 1, it increases for the rest of eternity because of that arrow. So anywhere greater than 1. We've answered that one, and we've given a full explanation. Lastly, identify all local maximums. Again, I can explain before I even look at the graph. Where do we get local maximums? For these values of x, let's see, I always have to think. Maximum is like this. So it's where the derivative goes, where the function goes from increasing to decreasing, so where it's the derivative goes from positive to negative. F prime of x goes positive to negative. We got our points for getting the right reasoning, and now we have to look. Where does it go positive to negative? Positive. Ooh, it looks like it was going to go negative, but it doesn't. It gives a 0 slope. But right here, at -1, it goes from positive to negative. So you'd say, at x equals -1, and there's no other places. That would be a local minimum at 2 because it's going from a negative to a positive. So I guess I should put, for this, there's only one value. So for this value of x, f prime of x goes from positive to negative. So we knew if we were to graph the actual function, we would know right here we have a local maximum. And right here we would have a local minimum. So I think what you're finding is all of these ideas can be tested in different ways to see if you understand it. And the more ways you do it, the better you're going to understand what the derivative tells us about the actual function. And that's one of the most important things in a calculus course. So keep practicing and thinking about these ideas, and it'll just become more comfortable all the time. So thank you.